Greetings people, welcome back to the Intoxication calculus. This video will extend on the previous video about limits, so today the topic of discussion will be the specific laws of limits. Without redundant introductory discussion, here are the laws of limits. Essentially nothing special, just the same simple arithmetic rules that you use for addition, subtraction, multiplication, etc. This may look indeed surprising because probably you would expect calculus and limits to look very complex and sophisticated, perhaps something like this. But apparently it turns out that limits are just simple kindergarten math with subtraction, addition and stuff like that. Nothing special. In general, you can even use just direct substitution for polynomial and rational functions, since the value of limit will be just equivalent to the value of the function at x. In cases of solving limits for simple polynomial functions, it's extremely annoying to have this limit notation clinging onto you and not allowing you to solve everything fast and properly just by simple algebra. Therefore, for such simple cases, solving for limits becomes just simply plugging the values of a to which x is approaching into the function. So this is a very trivial example that you can easily solve by just using the addition law of limits. So here we have two functions, 2x and absolute value of x minus 3. Both of those functions are continuous, polynomial, and in this case we can just have direct substitution and nothing really interesting happens, so that's it. It's 6. Obviously you won't get such simple problems most of the time, because the purpose of calculus is not to entertain people with regular algebra, and rather you will get functions which are not defined at a certain point because they have their denominator which has a 0 value for a specific x. So in this case, most likely you will be asked to find the value of limit, specifically as x approaches that point where those functions are not defined. And surprisingly for calculus, you can actually cancel out the 0 terms in these cases. In regular math you wouldn't do anything like this, obviously, because math teacher will be justified to do something like this to you. Because forgetting about the restrictions of the functions and holes in the graph is obviously not excusable.
오늘부터 종업식 때까지 교실은 물론 교무실까지 청소야.
But you're allowed to do this for limits when x approaches something that will give you a value which is not defined. Why cancellations are justified? So if you have two functions which are almost identical except for the value of x at a, then you can say that those two limits are equal to each other when x is approaching a. Besides this one single exception of the general algebra rules, the algebra of limits is limited to the standard procedures of solving algebraic equations. Few other trivial examples which you will do a lot when you solve limits. So in this case we just have a difference of squares, which is quite simple. Then we factor out the denominator, and you have to always remember about this limit notation, which is really annoying, that you have to write limit of t as it approaches -3. Always remember that, always write that, and that's it. You just substitute -3 into this equation and you get something like this. Nothing interesting. This is another boring example. In this case you just open the brackets of square, just bring to the square this term of h plus 2, and after that you will notice that the 4 will cancel out. In this case you can cancel out h, so you won't have anything annoying and any obstacles in your denominator like h. After that you plug 0 into h plus 4 and you get your answer. Just regular algebra manipulations. The hardest limit problem that you will ever get will be probably some really perverted algebra problem. As you can see, subbing 2 into denominator will result in 0, negative 2 will result in 0, so in this case you just need to have your numerator factored in such a way that the redundant term in the denominator will be cancelled, so there won't be anything that will result in 0 in denominator. In other words, you just need to get rid of x plus 2. So you need to have your numerator divisible by x plus 2. So for this case, you will need to employ long division. And yes, even though you have two variables in numerator, you still can perform long division, because in this case, coefficient can be anything. It doesn't have to be specific number. It can be just some variable like a. So we perform long division first. First part is really simple. We just divide everything by 3x. And for the remainder, we will have a minus 6 multiplied by x, because we just have x factored out. Then you just multiply x plus 2 by a minus 6 to get rid of x multiplied by a minus 6, and you will get a remainder eventually. As you can see, it's a very, very long division. It takes a lot of time. Oh yeah, it's negative sign there. It's really easy to make mistake. Probably the thing that you will do often. So as you can see, the remainder is 15 minus a, and for this reason you need to have a, so the remainder will be 0, so it will be possible to cancel out everything, and it will be possible to factor out the numerator. That's why a becomes 15, and we know that the remainder has to be 0. Yes, correct. So then, if you are really interested in finding the limit, you can just use simple, very, very simple substitution. You know that the other term of the factored numerator will be 3x minus, plus 9. And then you just cancel out x plus 2. And that will leave you with some answer, like negative 1. That's the limit of this. That's the limit that will exist in this case. The only situation where the limit will exist, actually. And at the end, you'll probably need to know about, to be honest, quite useless theorem, which states that if for each value of x of the three functions which satisfy the following conditions, and also if one of the conditions is that the limit of f of x and g of x is the same at a, is equal to L in this case, then the limit of the central function of hx will actually be also equal to L. Visually on the graph, this function indeed looks like two functions squeezing one other function into a specific point. That's why in most of the oppressive and totalitarian countries this theorem is known as the Theorem of Two Policemen, like in Russia, for example, People's Republic of China, and even France and Italy in the European Union would be considered as totalitarian countries according to this metric, while the liberal democratic Western English-speaking countries prefer to call this theorem squeezing theorem. As I mentioned, this theorem is really useless. You won't use it very often, but there are some few very beautiful examples where this theorem works perfectly. So for example, consider finding the limit for this trigonometric function multiplied by square function. Therefore, referring to the Squeeze theorem and keeping in mind that the sine function always oscillates between -1 and 1, you can come to conclusion that the functions of x squared and -x squared will be always greater and less respectively than the function that interests us. And thus, considering that the limit of those two functions, x squared and -x squared, at 0 is equal, it's actually 0 as well, then it becomes clear that the limit of the function of our interest is also equal to 0. A common opinion among people who study science and math is that people who study arts, liberal arts and social sciences basically study useless things. And those sciences are deemed to be useless only because they don't have enough math in them. That is actually incorrect. Even though I can't really account for all of the social sciences, and especially Hispanic, transgender, gay and lesbian studies, I can assure you that history still has some connection to math. The proof of it is that the outcome of World War II was easily predicted by the Squeeze Theorem. As you can see, due to the fact that Nazi Germany was constantly oscillating between two battlefronts of Western Europe and Eastern Europe, it eventually lost the war, and the two battlefronts of USSR and US and Western allies actually forced the Nazi Germany to limit itself exclusively to Berlin. And as USSR and United States are fighting over the coordinate of real numbers, some were far away in the coordinate of complex and imaginary numbers. China is on the rise. That's it for today, ending with this nice Asian invasion. We thank you for watching this video, and stay tuned with Intoxication, or shall it be called on this occasion Bubble Tea Intoxication?